Our presentation is on the flows in porous media as they relate to the protein purification process. We are Team 12. And we first wanted to start off with a brief explanation of what is porous media. And at a high level, porous media is simply solid material that has internal voids. And this material can take on several different kinds of structures, some of which are represented by these photographs below in the bottom left. And they're listed as a foam structure, which is basically a sponge, granular structure, which is like sand, and a fiber matrix, which uh, is similar to plant tissue. And all these different kinds of porous media will have different characteristics, and we characterize the medium in the following ways. The first way is with the specific surface, and this is essentially a measure of the total interface area between the void space and the solid phase. And then over here on the right, epsilon is the porosity of the medium, which is given by how much void volume there is compared to the total volume. And then there's the available volume fraction given by KAV. And the available volume is the volume of the void space that is accessible to a flowing solute. And what's interesting is that this available volume is not necessarily the same as the total void volume. And that has to do with the physics of the different pores within the medium. For example, if the opening of the pore is smaller than the solute, then the solute will not be able to pass through that particular pore and it won't be part of the available volume. And we also can characterize the medium with its tortuosity, which is a measure of how much the pore path deviates from its shortest theoretical path. In other words, it's how twisty and windy the pore is within the medium. And when we're characterizing how fluid might flow through the porous media, this can change depending on the permeability of the medium. And so starting with super low permeability, where it's shown here in this illustration in the bottom right, where the fraction of solid phase is extremely high compared to void space. We can use Darcy's law to model this type of system. And Darcy's law given here in the bottom left, if the gravitational term is neglected, it shows that the velocity of the fluid is proportional to the pressure gradient, where the constant of proportionality is the hydraulic conductivity. Darcy's law assumes homogeneous flow and is not applicable for non-Newtonian fluids, for Newtonian liquids at high velocity, or for gases at very high or very low velocity. Darcy's law also assumes that the viscous effects within the fluid are negligible compared to those between the fluid and the solid interface. When the permeability is higher, or when the solid phase, there's less solid phase and more void space, then that assumption that the viscous effects within the fluid are negligible may not be applicable. And as a result, for this system on the left, we may want to use the Brinkman equation to model the fluid flow. And the Brinkman equation is very similar to the Darcy equation, and it has the same terms, but it also includes this mu del squared V term, which accounts for the viscous effects within the fluid. And when the permeability of the medium is extremely high, where there's little to no solid, then the Navier-Stokes equation may be applicable.
We're going to be talking about the three types of chromatography methods for protein purification in this project. So on the left, we have ion exchange chromatography, which can be through cation and anion exchange separations. And in the middle, we have size exclusion chromatography, which is separation based on size. And on the third, we have affinity chromatography, which is separation based on affinity tags, such as nickel or his tag, and many others. And going to our next slide, these three types of chromatography methods that I mentioned before, they are types of packed bed chromatography, where the pressure drop in a packed bed can be modeled by Darcy's law, as we see the equation on the slide below. And the hydraulic permeability can also be found through one of the following empirical equations listed, such as Giddings, Blake-Cosney, Happel, and Jackson and James, where it depends on the inner particle porosity and the resulting specific permeability, as we see on this on the graph depicted to the right.
There are some limitations of packed bed chromatography. The already high pressure drop tends to increase throughout the process, leading to the media becoming compressed and pathways getting blocked by material. As you can see in the figure, transport depends on intraparticle diffusion. This requires extra time and buffer when compared to membrane chromatography. Cracking of the bed can lead to channeling where flow passages form, allowing short circuiting of mass flow. And most conventional materials are polydispersed, meaning they are non-uniform, which can alter radial and axial flow. All of these issues can lead to deviation between the models and reality, since models assume even packing, uniform materials, often spherical, and do not account for short circuiting. Some of these issues are being overcome by the development of new monodispersed, non-porous, rigid materials, such as the monobeads pictured here, but these tend to be more expensive and have lower solute binding capacities. And this doesn't address the increasing pressure drop issue. Synthetic micro and macroporous membranes have also been developed that transport solute to their binding sites mostly by convection as opposed to diffusion, leading to less process time and buffer use. For these type of materials, the binding efficiency becomes essentially uncoupled to flow rate. In our lab, we typically use Sephiros columns, which are material created by sativa from a cross-linked beaded form of agarose. The first type of packed bed chromatography we will go over is ion exchange chromatography, which encompasses both cation and anion exchange chromatography. Cation exchange captures positively charged proteins of interest using a negatively charged resin, while anion exchange captures negatively charged proteins using a positively charged resin. There are a variety of different functional groups that can be used depending on the overall charge and chemical properties of the proteins that you're trying to isolate. Within cation exchange, positive proteins within the mobile phase will bind to the negatively charged particles within the stationary phase. In the wash step, proteins that have gotten trapped within the porous media or lightly bound are washed out, leaving only the positively charged proteins remaining. In the elution step, a gradient of increasing salt concentration is applied to the column. Less positively charged proteins will be eluted in earlier fractions, while more positively charged proteins will be eluted later in the gradient. Each eluted protein will have a separate absorbance peak, and the fraction that your protein is in will depend on the overall charge of your protein and can be confirmed with an SDS page show. Since Fick's law is only applicable for low concentrations, whereas protein purification involves a high concentration of absorbed protein, it cannot be used to model ion exchange chromatography. Thus, the Maxwell-Stefan approach is often used, with the chemical potential gradient considered as a driving force of mass transport. This model is especially useful for multi-component systems that involve interactions. One thing to note about this equation is that activity is a dimensionless quantity that is a measure of effective concentration of a species in a mixture. For a pure substance, A is equal to 1. In order to investigate how well the macroscopic-based transport equations model microscopic behavior, this 2008 paper analyzed the transport pattern of a commonly used protein called BSA using confocal laser scanning microscopy, CLSM. First, they performed finite batch absorption experiments and fit the data to the Langmuir equation to find the absorption isotherm. The Langmuir equation treats the protein resin binding as a chemical interaction between an absorbent molecule and an empty sorption site. For two-component systems, many studies use the extended Langmuir isotherm instead. Based on those experiments, the dynamic absorption at 3 different salt concentrations was found. The retention behavior of the protein was then analyzed using the following equation. Intraparticle diffusive mass transfer was then modeled using this equation. The diffusive flux was then calculated for 3 different mass transfer models. The POR-DM model, or porous diffusion model, assumes primary resistance to mass transfer is diffusion through pores, while the SDM model, or surface diffusion model, assumes negligible pore resistance. The MDM, or combined model, combines both pore diffusion and surface diffusion. The corresponding Ds here are the diffusivities for each of the models. The finite batch absorption assumption was applied to all models. This model assumes limited contact between solute and absorbent in a finite volume. It assumes uniform mixing, but that diffusion occurs within the solid phase. It sets the change in protein concentration over time equal to 3 times the volumetric ratio of the solid to liquid phase over the particle radius times the diffusive flux at the particle radius. The initial concentration assumes an initial protein concentration of C naught in the bulk liquid phase, a concentration of 0 for the protein in the liquid-filled pores, and the protein absorbed into the beads. As for the boundary conditions, at the outer radius of the particle, the concentration in the pores is assumed to be the same as the concentration in the bulk liquid phase, and in R, the symmetry condition is applied. By using CLSM, it was found that the pore DM and MSM models work well in low salt concentrations, while the model that took pore resistance as negligible did not apply. However, at higher salt concentrations, especially when it approached 50 levels, pore DM, MSM, or SDM simulated the data very well. Studies on grafted materials have shown that pore accessibility increases at increased salt concentration, so this may be why, but Sephiros is not a grafted material, and the paper did not elaborate on why that may be. Other studies have looked into how pore size affects the flow. For Sephiroth columns, the pore size is big enough to not have a significant hindrance, but some other types of columns with smaller pores, especially grafted polymer columns, can result in hindrance of counter diffusion and thus protein displacement for a two-component system.
So now going into size exclusion chromatography, also known as gel filtration, size exclusion chromatography essentially allows us to separate molecules by their differences in sizes as they pass through a resin-filled column. Typically, a size exclusion chromatography column has two phases where we have a stationary phase and a mobile phase, where the stationary phase typically involves the resin beads, whereas the liquid continuously flowing through is called the mobile phase. So typically, size exclusion chromatography involves two different types of particles, where where typically one particle is too big to enter these porous resin beads, where they end up remaining in the liquid phase and elute quicker. So to visualize this, as we see on the picture to our right, we have our size exclusion chromatography column where the flow is going downward. And we have our porous resin beads that are labeled in blue. And we're dealing with two types of particles where you see red and pink, where you can see that the red particles are much bigger than the pink particles. So because of that, these red particles can't enter these porous resin beads. So as we've run this column, they end up eluting quicker, as you can see on this graph, where as time goes by, we see a red peak appearing first. But compared to these pink particles now, these pink particles can enter these porous resin beads. So they end up in the stationary phase for a longer time. And essentially, they elute later because they have more volume to traverse. And I also wanted to put a picture of exclusion chromatography columns you would see in like a laboratory setting where you can see that they differ in sizes and lengths, which kind of depends on the types of particles you're trying to separate. So now I want to talk about an important concept in size exclusion chromatography known as theoretical plates. So in general, chromatography columns that are considered to be made up of plates of a height h, where each plate is basically assumed to contain equilibrium of the mobile phase and stationary phase, where an important calculation is called the height equivalent to a theoretical plate, or the HETP, where it utilizes the Van Dimter equation. So this basically takes into account the shear effects and dispersion forces that we typically see from the Brinkman equation, which basically influence this HETP value. So this equation takes into account three constants, which is A, B, and C. So for A, it represents the eddy diffusion, which typically is caused by uneven pads in a packed column. And then we have B, which is longitudinal diffusion, which is basically from the solute spreading across the column due to random motion. And then we also have C, which basically involves the resistance to mass transfer of the analyte between the stationary and mobile phases. And lastly, we have U, which basically represents the speed of the mobile phase. So when you're calculating HETP for a size exclusion chromatography column, you basically want to minimize the HETP value, because if you minimize it, it basically represents a greater column efficiency, because it means that you need less length for the columns, which in a laboratory setting can translate to a reduction of cost for these columns, and you also end up seeing better separation.
The last topic we're going to touch on is affinity chromatography. Affinity chromatography is a useful technique when we don't know much about the specific properties of a protein of interest, but what we do know is a specific binding interaction between it and a particular ligand, which we do already know about. We take that adequate ligand and attach it to a solid phase, which is usually the highly cross-linked agarose beads that I've pictured here at the right and that we have talked about previously. The diameter of these beads tends to be on the order of 100 micrometers, but it can differ. And the pores that we can see in the bottom two pictures here are around the 100 nanometer range. We pack a column full of these tiny beads, which we then flow our proteins into. Proteins are essentially filtered through with the protein of interest being caught by the ligands and bound to the solid phase due to its specific interaction. To describe the total flow across the packed bed of our solid beads, we can use the Couseny-Kalman model. It is important to make the distinction that this model applies to the macro movement of fluid throughout the entire column and not the microflow through and around individual pores and beads. Here, phi sub s is a shape factor, also called a sphericity factor, that depends on the shape of the solid material packing the column. In our case, we have essentially perfect spherical beads, so we can take that factor to equal 1. What results is something we have discussed already, and that is Starkey equation slightly disguised. Here, the part of the equation enclosed as red is the effective model permeability K. As we can see, the effective model permeability is a function of particle diameter and column extra particle porosity. The other variables in the equation are U, surface velocity, L, the length of the column that we integrate our relationship over, mu, the dynamic viscosity, and delta P, which is simply the pressure drop across the column. There is, however, a special consideration to be taken into account when it comes to affinity chromatography. As proteins interact and bind to the ligands, which are already bound to the agarose beads, the solid phase, we find that these proteins take up space, obviously, and if the protein in question is comparable in size to pore dimensions, as is the case, for example, with immunoglobulin G, the most common antibody found in our blood, we find that they take up enough space to shrink the effective pore diameters and therefore intraparticle porosity. This phenomenon changes flow models and mass transport properties of the system as beads saturate with the bound protein. In particular, when we talk about mass transport, which is the more important aspect of protein chromatography processes, this behavior worsens what is known as hindered porous diffusion. This is a type of diffusion that occurs when one tries to flow a solute through a porous media, when the pores of the porous media in question and the solute are of comparable sizes. Again, the absorption of the proteins worsens this behavior as they become bound to the solid phase. In order to properly model the intraparticle, by which I mean inside the beads themselves, material transport of the system, it is important to ascertain a proper value for porous diffusivity, as the standard value of free diffusion will not be accurate. A general solution that describes this behavior is difficult to produce, and as such, scientists usually resort to empirical models, of which several have been proposed. Here are two, the Oxton and Boyer models. Oxton calculates the ratio of effective porous diffusion to free diffusion as a function of solid media filament radius, R sub f, and the hydrodynamic radius, also known as the Stokes radius of the protein, R sub s, of the bound protein. Boyer has the advantage of using molecular weight and a couple fitted parameters instead of particle and filament radius, as these molecular weight value is readily available in literature. Nevertheless, both models use filament volume, the root psi term, and when we take absorption into account, this actually becomes apparent filament volume, which is greater than what would otherwise be measured. In conclusion, we have talked about a few chromatographical techniques today and the mathematical relationships that govern them, starting with ion exchange chromatography, size exclusion, and then finally affinity. These expressions not only describe the flow of the fluid through the porous media of the columns, but also their particular interactions, such as ionic and covalent interactions in the case of ion and affinity chromatography. Affinity chromatography is actually the most widely used, especially for first rounds of protein purification, while ion exchange is often used for secondary rounds, and size exclusion is typically used for a third, final round, only if the protein needs to be very pure, such as for use in human cells, since there is a trade-off between yield and purity due to the loss of some protein at each step of the purification.